Okay, so this lecture is about infrastructure and tooling. And what I like to kind of start with is just thinking what the ideal deep learning process could be, and then where we are today, and then maybe seeing where the complexities are. So I think the ideal process for learning from data is that you just label some data, or you already have labeled data, and then you just get an optimal prediction system. It's 100% accurate on the data, does a good job on data you haven't seen before, is a scalable API if you're deploying to the web, or maybe it fits on your phone if you're deploying to mobile. Today, here's what you actually have to do. You have to aggregate the data, clean it, store it somewhere, label the data probably by hiring people, version the data. Then you got to write and then debug model code. Then you got to run a bunch of experiments because it's not enough to just get a model working. You also have to find the right kind of parameters for it, store the results somewhere, and then test the model and then deploy it to production. And then one thing that people don't often think of, but you actually also have to monitor the predictions that the model's making, and ideally kind of close what we call the data flywheel loop, which is you look at the data that users are actually sending through your system. You see what your model is predicting on them, and if it makes a mistake, ideally you get feedback from the user, but maybe you just hire a team of annotators to review all the predictions, or just low confidence ones. You label them, and you go back up, right? You take that as data back to the source, and you run more experiments, and you keep improving your system. So Google's been doing this kind of stuff for a while, not just for deep learning, but for all kinds of machine learning. And they've built up a lot of expertise and knowledge about how to deal with it. And their opinion is that machine learning is the high interest credit card of technical debt, meaning that you don't realize how quickly you accrue technical debt when you start implementing machine learning solutions. Technical debt, of course, refers to being able to ship a feature, right? But then you haven't paid entirely for the feature that you shipped. You have to, at some point in the future, go back and refactor the code you wrote, or start hiring more people to scale the code base. Then if you had paid down the full cost of shipping that feature right up front, then you would have no problem scaling it in the future. And in that paper, Machine Learning, the High Interest Credit Card, there is a striking figure, which I reproduce here, which is the amount of code in a typical machine learning system. And so the actual machine learning code, which for us would be in that models and networks folder, is a tiny fraction of the overall code base. There's a lot of stuff about, where's the data coming from? How do we extract features? This is more relevant for non-deep learning solutions, but at Google scale, you have to extract certain features potentially across multiple services, data verification. How do you actually allocate the training jobs to the machines you have? How do you analyze the model that you produced? How do you serve the model? How does the model serve predictions? And the monitoring of the predictions. Now, I like to break down kind of the landscape of the tooling and infrastructure that you might need for an entire machine learning code base. And I have this abstraction kind of so like down below you have low level abstraction stuff to high level abstraction. So it's broadly, there's things concerning data, things concerning your model development and evaluation, and things concerning deploying the actual model. In all cases, you have to make the first decision of like what are you actually using? Are you using your own servers? Are you using the cloud servers? And then for deployment, are you deploying to the cloud as a web API? Are you deploying to an embedded device? Are you deploying to a mobile phone? For data, there's the kind of bottommost storage layer. Like what is a file? Where does it live? There's the database, which is kind of an abstraction above files or potentially memory that lets you search and query your data. Workflow refers to data processing usually. So for example, if you have a multi-step process from converting your raw database data to something that's trainable, and you need to run it on some kind of schedule or asynchronously, that's referred to as workflow. Labeling is, okay, you have the raw data, but you have to label it so that you can actually train on it. There's services that help you do it, and there's software that lets you do it yourself. And then versioning is an important thing that I think someone already asked about, which no one really knows how to do well. But it's basically the idea that your data set is not static. It keeps growing, just like your code base is not static, and it keeps changing. We know how to version code. We just use Git, kind of what people converge to. But how do you deal with changing data? So versioning, there's some solutions, or there's some simpler things that you can just do. In the development and training of models, you have the base layer of just, can you write software? Text editors, Jupyter Notebook, Python, Git, stuff like that. We don't cover that. Frameworks, there's deep learning specific frameworks or even machine learning specific frameworks. Resource management refers to, OK, I want to train a model, but I want to use multiple GPUs. How do I actually do that? Or I have multiple GPUs in my single machine, or maybe I have multiple machines with a single GPU. Are those different? How do I actually manage the resources there? Experiment management refers to, OK, I have a model. I know how to run it on my hardware or in the cloud. But how do I actually store the results of all the experiments I'm trying? And there's a bunch of startups that recently came out that try to have a solution for that. Distributed training is specifically using multiple GPUs for the same model training versus just running different experiments per GPU. And then hyperparameter optimization is this idea that you have your network and your model, and you're training it, but should you be using 4 layers or 5 layers? Or what should your learning rate be? And do I just have to try all possible things? Is there a smarter thing I could do? For deployment, we have continuous integration and testing. You have your model already trained, but how do you know that upgrading to TensorFlow 1.13 is not going to break it, right? Or you push some code and it breaks a model that you're not even touching because you changed something about the data side of things. Web deployment, Amazon, Google. Monitoring, that refers to both, is the system up and is the system serving predictions that make sense? Interchange formats are, I train my model in TensorFlow, but I want to use it with PyTorch, or I want to use it on an embedded device that only has Caffe or something like that. And then hardware mobile has its own set of challenges, which is maybe a model that you trained on a GPU on your PC is just way too big to fit on your NVIDIA Jetson embedded board that you're actually trying to ship on. Or mobile, mobile phones, perhaps there's SDKs and frameworks that you can already use that are already on the user's phone. And then there's a trend of companies, big companies like Facebook, Uber, Google, Amazon, and also startups trying to solve all of these challenges in one go. And I call these all-in-one. And so that they don't necessarily have to hit all of these boxes, but some combination of multiple boxes. So for example, Domino Data Lab will give you a notebook environment and GPUs that you can kind of scale up and down with a slider, and maybe they even serve your model. I'm not sure. So in this lecture, for the next hour and 15 minutes, we're going to do development and training and evaluation of models. In about 2 hours, I'll do another lecture on data management specifically, and then tomorrow we'll do deployment. I think these are opportunities for tools that don't exist yet. So potentially, for example, in monitoring, there's solutions for monitoring running services like web servers. Am I answering a response that comes in? There's tools for that. But when you're serving model predictions, that's not enough to just know that your model is up and serving predictions. The data distribution might have changed. So you started getting different types of data, and the predictions you're serving are actually garbage. So I think there's an opportunity that I haven't seen met yet for a specific machine learning monitoring service. So whenever you see a question mark, I think there's an opportunity for a tool there. Or maybe I just don't know of a tool that works well. You guys have any more questions before we get going? OK. So software engineering is a prerequisite for this course. You should know how to use Python, Git, and a text editor of some sort. Frameworks. Last time we had a guest lecture from Yang Qing, who was my lab mate. He was a developer of Caffe and TensorFlow and Caffe 2 at Facebook. He gave a whole hour about frameworks. So there's a lot to cover. and I will not cover nearly as much. I just have really just a couple of slides, but I think I want to get the most important thing. So deep learning frameworks can roughly be thought of on two axes. How easy is it to develop in this framework? That's on the bottom, on the x-axis, good for development. And then once you develop a model, how easy or how scalable is it when you actually put it in production? And that's on the y-axis here. So one of the first deep learning frameworks was Theano and Torch and stuff, and I'm not putting that on there. But I think after AlexNet kicked off the deep learning revolution in 2012, one of the first deep learning frameworks to really get enterprise adoption is Caffe, which was actually developed by my lab group here at Berkeley, like 6 floors up from this room. And it's built in C++. To add a layer, you have to code it in C++ and code the backward step. You code the forward step, which is usually pretty easy, but you also have to code the backward step yourself, which means you have to do some math and derive the derivative of it. So it's not easy to develop. But because it is in C++ and because everything is so optimized, it is actually very good for production. And so even today, financial services and a bunch of real-time applications of deep learning are still using Caffe because it's so good in production. TensorFlow came out a couple of years after Caffe, and Caffe was just developed by really just like 4 people, grad students. TensorFlow is developed by something like 100 people, and now over several hundred people at Google. And it was a big push specifically to develop a system that is good for production and can be deployed to servers that are optimized for deep learning, servers that are just commodity PCs, even mobile phones. And so TensorFlow really tried to solve the problem of like write once and then run everywhere scalably. It is pretty decent at production. It is not a very good development experience because it introduces this abstraction of the computational graph. So when you write a TensorFlow model, you're not actually writing code that gets executed. You're writing code that gets compiled by TensorFlow into something that gets executed. And it's that conceptual step that makes it kind of hard to write that code. And it's hard to debug it because you can't just put a breakpoint in your TensorFlow model. It's not as easy as that because the code path is actually not in the code you wrote. The code path is generated from the code you wrote by TensorFlow. Keras came out as a kind of nice wrapper on top of TensorFlow and Theano, and then later MXNet, which is another kind of Caffe-like thing. And it focused on a good user experience on the development front. So it really pushed forward the good for development boundary. And because it's backed by TensorFlow, it's still pretty good for production because whatever you write in TensorFlow just gets compiled to a whatever you write in Keras just gets compiled to a TensorFlow graph. And there's not potentially as many things that you can write in TensorFlow as you can write in Keras as you can in TensorFlow. But whatever you can write in Keras is going to be just as good as if you had written it on TensorFlow. And then most recently, we have PyTorch from Facebook. Facebook had researchers that used to work on a deep learning framework called Torch, which is in a language called Lua, which no one knows how to use, but is apparently very nice. I don't want to, I don't want to badmouth it. But PyTorch was specifically the ideas of Torch, but in Python. And it's been phenomenally successful at being really good for development because you just write Python code, and that's the code that gets essentially executed. So if you want to put a breakpoint right in the middle of your model, you can with PyTorch. And that's very liberating, and it's really what a lot of researchers have shifted into because it is easy to make all kinds of like loops and crazy models and circular decision trees and stuff like that. Our recommendation is unless you have a good reason not to and you can explain to someone else why you're not, you should use TensorFlow probably with the Keras front end or PyTorch. And the reason I say either one is because they're actually both converging to the same, what I think, ideal point. And the ideal point is that it should be easy to develop it by just writing some code, running it, and then keeping track of all the gradients, backpropping automatically through it, which is what PyTorch is famous for. But TensorFlow also has the same functionality, or it will in TensorFlow 2.0, with this eager execution mode. And then on the other hand, PyTorch is really good at defining by run, but it hasn't been very optimized for different platforms. But they are resolving it, or potentially already have resolved it, by adding Caffe2, which is the successor to Caffe, which is also in C++, directly into the PyTorch code base. So what happens now is you define your PyTorch model by just writing code, but then when you're ready to productionize it, you compile it into an optimized graph, and that's executed using Caffe2. And because Caffe2 is just C++, it can run on anything. It can run on your phone or anywhere. Anecdotally, like we've all met people who are happy that they switched to PyTorch, and I personally haven't met people who've switched away from PyTorch to something else, and we're happy about that. So take that for what it's worth. Google searches, people are searching a lot for TensorFlow and Keras, definitely. And in our interviews so we did like 20, 25 interviews with deep learning practitioners in preparation for this. Most people use TensorFlow and Keras, but PyTorch is definitely growing. These are job posts, though, and TensorFlow is definitely #1. But then, Caffe is still up there, and that's because a lot of kind of more boring industries, I guess, like oil and financial and medical stuff, are using Caffe still because it's so fast and because people kind of learned it and they're OK with C++. So that's all I have to say about frameworks. Do you guys have questions? Yep.
What is your opinion on Swift on TensorFlow? Why do you think they're deploying?
I have no opinion. I don't know much about it.
What was the question?
Swift on TensorFlow. Or is Swift a good language for doing deep learning? I think the usual answer is give it a couple of years to settle down. So yeah, I think if you're a Swift enthusiast, then it's probably a great language. But if you're not, and you're thinking about learning Swift just to do deep learning, it doesn't make sense right now because it's not clear whether it's good or not yet.
How about Julia?
Yeah, that's interesting. So Julia, I think, is seeing a lot of energy put into deep learning frameworks. And I was really excited about Julia when it was first announced 6 years ago. But it never seemed to really gain adoption to the same degree that Python has. I think the ecosystem is just so powerful around Python that it's going to be hard for some time yet to switch away from it because there's just great libraries for pretty much anything you want to do. So if all you want to do is train deep learning models, then maybe Julia is great, and even today. But if you have to interface with all this other code and munch data and maybe deploy it and stuff, then Python's probably still better.
How would you compare the learning curve for TensorFlow and PyTorch? Which one is it?
Oh, PyTorch is definitely easier because it's just Python code. So once you understand the concept of there being something keeping track of the gradients of the code that you run, then all you have to do is just write the code and then not worry about anything about the gradients. Whereas in TensorFlow, you really have to understand the computational graph right away to be productive in it. Now, Keras, I think, is even simpler, though. So Keras is what we use in lab here. And I think that's the simplest. I would say Keras, then PyTorch, and then TensorFlow. So the next thing I want to say is when you're doing development and training and evaluation, you have to pick the hardware that you're going to use. Are you going to use your own on-premise hardware? Or are you going to use the cloud? So how do you even think about what you need to do deep learning development? I like to split it into two conceptual pieces. The first is the actual model development. The second is the training and evaluation of something that you know can run. And so the idea is when you're developing, you're writing code, the code you wrote isn't working because it never does, so you have to debug it. And then you have to look at the results just to make sure you're on the right track. And what you want to do is you want to just quickly compile models, run quick training, probably be able to use a GUI of some sort to look at the results. And I think an ideal solution is actually just your own desktop with a few GPUs in it. But if you can't have your own desktop, then probably a dedicated cloud instance with a few GPUs on it is the next best thing. And then when you have something working, you potentially want to scale out your experimentation. And it worked with some set of parameters. And now you want to just search over different parameters and see if something works even better. Or potentially, you've been working on a subset of data, and now you have to apply it to your whole data, and it just doesn't even maybe fit on your machine. So there, I think it's important to be able to easily launch new experiments. review results at scale, so not just like predictions on one instance, but actually outputs of multiple experimental runs. And I think the solution there is maybe just more GPUs in your own machine, potentially just local machines that you can log into or just distribute jobs to. Or here you go into the cloud and you start running in the cloud. So how do we decide? Should we buy our own hardware? Should we go into the cloud? So in order to kind of inform you how to decide, I mean, there's never a one-size-fits-all solution, so you'll have to decide for yourselves. I want to cover some decision inputs. So the first is just what are GPUs, what are the basics, the cloud options, like what are the options actually for using GPUs in the cloud, and then what are the options for using GPUs on premises. And then my analysis and recommendations will follow. So the GPU basics is that NVIDIA has really been the only game in town for a while, but Google is actively pushing to unseat them, specifically for deep learning. And the Google tensor processing units are currently the fastest option for deep learning of most network types. And you can use them on the Google Cloud Platform. You cannot buy them and put them in your own machine. And then Intel is working on some cool neural network processing units. AMD GPUs could start making sense soon. But right now, it's pretty much NVIDIA. That's what we focus on here. So they tend to release a new architecture, which means like a new chip fabrication process about every year. And went from Kepler, Maxwell, Pascal, Volta, and then Turing. So it keeps going up in the alphabet and famous scientists. So first they release a server version. Then they release like a super expensive like enthusiast version for Bitcoin miners and deep learners. And then a consumer version for gamers. So for business, you're technically only supposed to use the server cards. So if you're using NVIDIA GPUs to like make money in some way, you should be buying the server version and using those. But it's commonly, that rule is commonly disrespected, I would say. So I have a whole table of different GPUs, and it's a little overwhelming. But we can break it down by architecture. So the earliest is Kepler/Maxwell, and it's the card in your cloud instance is actually a K80. So these are very much still in play. A lot of the cloud options, like P2 instance on Amazon, is a K80, or Google Cloud Platform, the default option is a K80. So they're still in play, even though they came out 5 years ago, or 4.5 years ago. So they're pretty decent. They're just kind of slower than what you have today, but they have a lot of memory. You can definitely make them work. They're 2 to 4 times slower than Pascal Volta, which is now not even the current architecture. So they're really, I would say, 6 to 8 times slower than the current architecture. And my recommendation is if you're building your own machine, just don't even buy them. But if you're using in the cloud, then these are the instances that are way cheaper than the current architecture. And that's what you'll probably end up using, because the current architectures are just so expensive. And that's maybe a segue into when you buy your own hardware, you're stuck with it for a while, right, until it fully depreciates on your balance sheet. And so people say, well, if you go into the cloud, then you're always on the latest version. But that's not true. Like the cloud providers also buy millions of these GPUs, and they're also stuck with them. So on the cloud, you will also be using these old ones, I think. So I don't think it's a good argument. Pascal Volta is the next architecture. So we've got the Titan XP, 1080 Ti, and then the V100 and the Titan V. So this is kind of like the past crop. And 1080 Ti used to be the sweet, or it is the sweet spot in this particular lineup. Titan XP is like 20% faster, but twice as expensive, so I don't think it's worth it. Titan V is 3 times as expensive, very expensive. And then the V100 is the current best server GPU option out there. So it's really the fastest server option today. And then just in December, they came out with a new architecture, and it's the 2080 Ti and the Titan RTX. And so this is the preferred choice right now, because it's not that much more expensive than the 1080 Ti or the Titan XP, but it is much faster. And so it's about twice as fast as a 1080 Ti, the 2080 Ti is. And then the Titan RTX is like 20% faster than the 2080 Ti. So this is what you should get if you're getting GPUs. Here's a cool plot about performance. So higher numbers are better. The TPU just dominates the ranking. The V100 is right below it. The Titan RTX / the Titan V is right below that. And then you got the 2080 Ti. So if you get a 2080 Ti, that's actually pretty good. It's like, almost as good as the server version right now. And then the 1080 Ti is now kind of towards the bottom of the list. So what do the cloud providers have? And who are they, right? So I think you really have three main options. You got Amazon, Google, and Microsoft. Those are the three. There's some startups that also do GPUs like Paperspace, but I think it just makes sense to kind of pick an ecosystem and try to live in it instead of trying to go with a startup. They might go out of business. If you're building your own company on this kind of compute, you should pick one of the heavyweights. They're largely similar in both function and price. I would say AWS is, like, all things being equal, slightly more expensive than the other ones. And then GCP has a super cool feature which actually lets you totally decouple the GPUs from the CPU and RAM. So on AWS, they have like some preset options. And so if you want 4 GPUs, you're getting 64 gigs RAM or whatever on your machine, and you can't change it. On Google, you can fire up an instance with 256 gigs of RAM and then connect 2 GPUs to it or something like that. And it also has TPUs. So I think GCP is the actual current winner for deep learning compute. And interestingly, like, machine learning is where they seek to differentiate between each other, because Amazon's the clear market leader in cloud computing. Everyone knows that. Both Google and Microsoft are trying to catch up, and they both see specifically the deep learning use case as like a wedge to kind of get there. And I'll talk more about this later when I talk about all-in-one solutions. So on Amazon Web Services, you got a choice between the V100 and the K80. And then kind of, it's all expensive. That's the first part. But then the second part is, if you're okay with spot instances, you get like a 50 to 80% discount. Now, a spot instance means that it can unexpectedly terminate at any time. So it doesn't really work well for you doing development, because you don't want to lose your work, and you just kind of want to know that you have at least one GPU always available. But it could work very well for experiments, right? So if you have a framework that lets you launch a bunch of jobs on spot instances, it's potentially okay if some of them get killed, because you don't even necessarily need all of them to finish. You're just kind of doing some hyperparameter search. So the thing there is that you need extra infrastructure to handle these failures. Google Cloud Platform, you got a choice between the V100, the K80, and then the P100, which is like a Pascal server GPU. It's cool that they can be attached to any instance. It's a little cheaper than AWS, and they have TPUs, which are cool. So I'm going to skip that. Microsoft has the V100, the P100, the K80, once again, about the same prices, pretty much equivalent. The spot instances don't seem to be as well kind of developed as they do on AWS or GCP. So maybe before I go into on-prem options, do you guys have any quick questions? I think one question is, like, do I have to pick one and live with it forever? Or can I be kind of agnostic as to what I actually, like, I just commit to using the cloud, but I don't care whether it's Google or Microsoft. Can I easily switch between them? I think the answer is not truly, like, kind of, but not really. So I think if you're picking a cloud provider, you should expect that you'll be locked into that cloud provider. Yeah.
You said that the spot instances, they require infrastructure because like you go down. Are we going to go into that and all the different options for that, or no?
No. Well, I'll cover some options, but not too in depth. Yeah, cover some options.
What's the trade-off between buying something like you said the 2080 Ti is about twice as fast as the 1080 Ti?
Mm-hmm.
What about getting two 1080 Ti's versus one 2080 Ti?
Yeah, so that kind of depends on. So there's two variables. There's the amount of RAM memory that the GPU has, And then how fast is it? How much compute can it push through, right? So the RAM is more or less a hard constraint. Sometimes you'll just encounter a model that just doesn't fit on a single GPU until you get a GPU that has enough RAM so that it can. So if you know that you're training like huge NLP models or something and you need a lot of RAM, then that's a constraint. And then now that you've satisfied that constraint, you can look at speed, right? So the 2080 Ti has 11 gigs. So does the 1080 Ti. It also has 11 gigs. So they both are going to be able to fit the same network. Like the same networks will fit on either a 2080 or a 1080. So then the question is, do you want speed, right? If you are willing to pay twice as much for twice as fast, then you should do it. If you'd rather just run more experiments and you don't care when they finish, then you can get two 1080 Ti's and run twice the number of experiments. But you can't easily buy two 1080 Ti's and have them be equivalent to a card that has 24 gigs RAM. So the RAM doesn't stack up, right?
If you choose cloud, where would you store the training data set if you're running multiple?
Yeah, I think I have some slides, so maybe I'll just start going to that. So actually, after the on-prem options, I'll get to like where to store the data.
Which one is more secure?
Yeah, I actually have a slide about that as well.
So, can you give me some ideas about cost, like how much, when does it make sense?
Yeah, I have slides, so I'll just keep going. On-prem options. I have slides for all this. Yeah.
Can you tell where Colab lands here?
Oh, yeah. So Colab is a Google Cloud thing where you get a Jupyter notebook with a GPU attached to it. The GPU is a K80. So that's where it lands, I guess. And it's ephemeral, meaning that, like, I don't think once you open a Colab, you just get to keep using it forever. You probably have a time limit on it. And if you stop using it, it'll time out. What's that? Yeah, so it has a K80. It's ephemeral. So it's kind of like a K80 spot instance is what I would say. All right, I'm just going to keep going because there's a lot to cover. So on-prem options are build your own machine. You can do that with up to 4 GPUs. It's easy to do. It's a quiet machine. Doesn't get hot. You can buy pre-built machines. It'll cost you more, but it'll also give you less headaches. Lambda Labs is the dominant startup building machines, but you can also buy them directly from NVIDIA, and you can also buy them from old-timers like Supermicro and Surascale. They build servers with GPUs in them. So building your own is kind of fun. I think it's a rite of passage for deep learners. I would encourage you to do it. You can build like a nice quiet PC with enough RAM to fit like most data sets, and 4 1080 Ti's. I actually think I meant to say 2080 Ti's here. I think it's actually 2080 Ti's. You can do it for $4,500. Oh, sorry, no, never mind. So 1080 Ti's is $4,500. 2080 Ti's boosts you up to $7,000. Probably take you like a day to figure everything out. If you want to have more than 4 GPUs in a machine, very painful because now you have to have a different form factor. Buy a server-grade motherboard, server-grade CPUs. Gets a lot more expensive, gets loud usually. So don't do that. And Tim Detmers has an amazing guide to building a machine, like talks you through the different choices you should make as far as CPU, like what do you need to look out for. So just go to this. You have the slides. If you want to buy pre-built, NVIDIA is really, I guess, the brand name, and it comes at a cost. So they used to have a machine with this exact form factor called the Digits Dev Box, but they don't have it anymore. What they have now is they only have machines with the server-grade CPUs, right? So the P100 or the V100. The reason for that is their own end-user license agreement. If they're selling something that's meant for deep learning, in a business setting, they can't be putting 1080 consumer-grade cards in there because it goes against their own end-user license. And so for that reason, they use the V100, and it's very expensive. It's $50,000 for 4 V100s, which might pay off if you use a lot of cloud computing. For pre-builds, we have a startup called Lambda Labs. And they still use consumer-grade cards, even though they very explicitly market to deep learners. So it's probably fine. You got a 1080 Ti option, a 2080 Ti option, a Titan V option. Like I said, it's basically, if you took all the hardware components and just purchased all of them on Amazon yourself, it'd probably be about 50% of the cost that they're charging. But you would have to set it up. If it breaks, you have to figure it out, fix it. And so here, they give you some warranty. They build it for you. They install the software you need. And I think it's probably worth it if you are in a company or you're buying many machines. But if you're just an enthusiast and it's a hobby for you, then I think you should build your own because it's fun and it gives you the experience that you really can't obtain any other way. They also have a 8x GPU solution. As you can see, it's now in a server-grade chassis. And it's probably super loud, so you would have to actually put it in a co-location facility instead of just next to your desk. These guys are quiet. These guys can just be right under your desk. It's totally fine. The cost analysis, someone asked. So I think we can build an on-prem machine that's the same specs as a cloud machine, and then see how long it would take for it to pay off the setup cost, right? And then we can also consider spot instances, because spot instances is a game changer, right? We can't, that's the one thing we can't do when we buy our own hardware. We can't just buy 100 GPUs and return them the next day. So let's say you're building just a quad GPU PC versus a quad cloud PC. So let's say you're using the Titan V so in your own build, you're using the Titan V. In the cloud, you're using the V100. They're roughly comparable. So if you kind of add it all up, if you run it for 24/7, how many weeks would it take for the cloud to exceed the cost of you just building it? And the answer is 7 weeks. So if you build this machine and you get 7 weeks use out of it, then you're better off than if you had decided to go with a cloud solution.
Does that include the cost of electricity?
It does not include the cost of electricity.
And these are not for spot instances.
These are not for spot instance. Yeah, this is a reserved instance. Yeah, so it's the idea is that a new data scientist has joined your company and you set them up with a 4 GPU machine. You have a choice between buying one or building it yourself or just giving them a persistent cloud instance. How many weeks would it take for the hardware that you purchase to essentially pay for itself in terms of cloud spend? And the answer is 7, right? So that's a 24/7 use, which is unrealistic. I also give you well, what if you only used it for 16 hours a day for 5 days a week? How many weeks would it take then? And it's 15 weeks, which I think is still makes sense to buy hardware. What if you just want a single GPU instead of 4 GPUs? Then the economics are slightly more favorable for the cloud, but it still just takes you 11 weeks of running it full time for you to just, for it to make more sense to just buy the hardware yourself. I don't account for electricity. I actually used to work at a building that didn't charge us for electricity, so it was great. So what about if you have a quad PC, so you're running some experiments on just your PC, versus you're going to build, you're going to start using spot instances to do it. So what we can do is we can just see the price of building out a quad GPU PC. We can see the price of getting a preemptible instance, a spot instance. And then what I think the way you should think about it is you can run 100 experiments, let's say. Let's say each experiment takes 6 hours, right? With spot instances, you could run 104 experiments in 6 hours because you launch all of them, right? You launch all of them, and they all finish in 6 hours. And that will cost you as much as if you had built that PC. But if you had built that PC, you wouldn't be able to run 100 experiments in 6 hours. It'd take you 600 hours. So I think the way to think about on-prem versus spot instances is how important is it to you to get experimental results quickly. It is expensive, but it might be worth it if you can just really scale out a lot of experiments at once. So other considerations that some people brought up is, well, where's your data, right? Maybe all your data is already on-premise, and it's terabytes of data, and you just don't want to send it up to the cloud. Well, maybe that's an argument for on-prem. On the other hand, what if all your data is already in the cloud, and it's over terabytes, right? You don't want to download it down to on-prem just so you can do deep learning. At that point, I think it makes sense to stay in the cloud. If you're downloading an academic image or academic data set or gathering a new data set, I think it's still a green field. Like you can decide, you can gather all your data on-prem or in the cloud. But if you're already locked into your data being in one or the other, then that's a consideration. Some people have concerns about data privacy. So, some data just cannot be uploaded to the cloud. A lot of financial companies just don't touch the cloud for that reason. And so then, well, you just have no choice, right? But I've also heard it the other way. Some people think that they've really nailed down security in the cloud, but not on-prem. And so for that reason, they don't want their data living on-prem. They only want it in the cloud, where they can like tightly gate access to it via SSH keys and stuff like that. So that's the security part. You guys have any questions about that?
Or if you want to store it in like cloud storage or hard drive, even your instance, attached to your instance, does it matter like which one is faster or something like?
Yeah, so I think the question is, are cloud hard drives as fast as on-prem hard drives? Or is cloud data transfer as fast? Is that what you're asking?
Use S3 or cloud storage to store your data. Is it going to be slow? Like, do you need to bring it down to?
So in the data management lecture, which is in a couple of hours that I'm doing, I will talk about kind of data locality a little bit. So maybe it'll just be addressed then. If not, then just ask again at that point. So I think in practice, most people we interviewed are on-prem. And those who are not on-prem often had tasks that are not GPU bound. So for example, reinforcement learning, like OpenAI does a lot of reinforcement learning, not necessarily using GPUs. There's a lot of like kind of experiments that you launch just with CPUs, or a lot of data preprocessing or something that is CPU bound instead of GPU bound. And that I think there it's more cost effective to be in the cloud. Or they had security concerns about, like, they just didn't want stuff to be on-prem. They already had it figured out in the cloud. So my recommendation for development, you got to build your own PC. If you're an enthusiast, great experience. For training and evaluation, you might get pretty far just using the same PC, maybe scale it out with a couple more GPUs. If you have a team of people working, you could cluster their PCs and then have a workflow manager on top of it. Or even buy PC specifically for running experiments on. But if you're running like a lot of experiments and it otherwise makes sense, or you have some other constraints, then I would recommend the cloud. So the basic reason to not recommend the cloud is cost. It's just the GPUs are very expensive in the cloud. Yeah.
If doing hyperparameter searching is kind of a normal part of any deep learning process, when would you not want to run hundreds of experiments, or at least dozens?
If you get performance you're happy with just a few experiments, then there's a cost and benefit trade-off to everything. Like, what is the marginal return on firing up another 100 experiments, right? Or even another single experiment. If it's low enough, then it probably doesn't make sense to do it. Like, you can always get a tiny bit better, but at some point, you have other concerns, right? Cost, the user experience. The user experience might be just as good at 80% accuracy as it would be at 82% accuracy, right? So the next thing I want to cover is resource management. And the idea there is you have multiple people, right, potentially using multiple GPUs or even multiple machines. They might be running disparate environments. Like some people use Mac, some people use, well, that's too much. But some people use TensorFlow, some people use PyTorch. We want to be able to easily launch a batch of experiments and then have each experiment have the proper dependencies, have the resources allocated to the experiment that are needed for it, and have that all happen like as seamlessly as possible. And the solution are, the first one is embarrassing, is just a spreadsheet. You could run some scripts. Then you can use something like Slurm, which is a workflow manager for just distributed computing, Docker and Kubernetes, or some specialized software specifically for machine learning. So spreadsheets is still surprisingly common. And the idea is that I'm working on, I got 4 GPUs in my machine. Josh has 4 GPUs on his machine. But I have a deadline this week, and Josh doesn't. So I might just use his GPUs. But in order to do that, I will just kind of let him know. And very common in research groups, surprisingly common even in companies still. And that speaks to the fact that there is no great solution to like allocating resources. People just are not able to find the solution that is perfect, so they just use something that's definitely not perfect, but at least works. Scripts, like what we're trying to do is just allocate resources that are available to programs that need them. And that doesn't actually need to be that hard. So you could just write a script that does it, at least for your use case, and have it be very effective. And actually, this is what we are going to do in lab in just an hour. Just have like a simple script, distributes experiments over the GPUs that are available on your machine. And you could, yeah. The kind of scaling out of that idea is to use essentially scripts that someone else wrote over decades, which is the Slurm workload manager. So it's like an old school thing for essentially distributing work onto clusters of machines. And like a GPU is just essentially a flag on a resource. Like, does this resource have a GPU? If it does this job need a GPU? If it does, then Slurm can match them up and be very effective at it. So the basic idea is that when you're ready to start training, you describe the resources you need. So you might say, I need 4 CPUs, 12 gigs of RAM, and 1 GPU. And then you submit a bunch of jobs to the Slurm queue. And then the Slurm manages all the resources. So the only way to submit jobs is via Slurm. And so then it starts running through the queue, distributing jobs, allocating GPUs.
So does this only happen when you're going to start like a training session, or can it reallocate mid-training?
I don't think it can change the resources it needs after the job has started. So I think you tell it what resources it needs. It'll allocate those resources to a job. Then the job either finishes or fails or completes. Yeah. So Docker and Kubernetes, we're going to spend a lot more time talking about Docker tomorrow. So I don't want to get too deep into it. But basically, it's a way to package up your entire dependency stack in something that's lighter than a virtual machine. So a virtual machine includes the operating system. And then Docker basically assumes that the operating system kind of exists and then packages up everything else. And because it's so easy to do that, people have started using it very much. And then Kubernetes is this idea that you might have multiple Docker containers, and then you want to deploy them. You want to run like jobs that are defined as Docker containers on some set of resources. Kubernetes is the interface between the containers and the resources. So we're going to talk about it tomorrow more, so I don't want to talk too much about it. But essentially, Kubernetes came out of Google. It has very wide adoption because it has a pretty nice interface. And fun fact, when you fire up the lab environment, that's actually Jupyter Hub. It's a Docker container that has Jupyter Lab in it on top of Kubernetes. So Kubernetes is allocating GPUs to your instance. And the idea is great of Kubernetes. You got worker nodes, master node, and then you can just submit a bunch of jobs and have it all be allocated. But the execution is very complicated, at least for now. So this is like the GitHub README of some project, like the best project for running TensorFlow experiments via Kubernetes. There is a startup called Rise.ml, which is kind of like a lightweight layer on top of Kubernetes that is specifically for deep learning workflows. So it makes it very easy to launch a whole bunch of experiments on top of Kubernetes. And then also, Google came out recently with something called Kubeflow, which is kind of like TensorFlow workflow in Kubernetes. I actually have a slide about it coming up. So do you guys have a question about resource management? So, yeah?
These tools for resource management, do they work easily on just multiple GPUs on a single computer, or can
Yeah,
merge together 2 local machines?
yeah. So it depends. Like the script works very well on a single machine. Slurm might actually be overkill for a single machine, but it works fine. But it'll also work fine on multiple machines. And then this Docker and Kubernetes only makes sense if you have a bunch of machines with disparate resources. So it does not make sense to run your stuff in Kubernetes locally. It just doesn't. And then RiseML is something on top of Kubernetes, so it also only makes sense when you have that scale. Distributed training refers to using multiple GPUs or potentially GPUs over different machines to train a single model. So far, I've been kind of assuming that we're training multiple experiments, like we're running multiple experiments. Each experiment gets a GPU, and that's the task we're trying to do. We're just trying to allocate GPUs to experiments. But sometimes you want to actually allocate multiple GPUs to a single training experiment. That's called distributed training. And I would say historically it has been less useful than just running experiments in parallel. So like if you had a choice between allocating 4 GPUs to a single model training session versus just running 4 different model training sessions, I think it has made more sense to just run 4 different sessions because you learn more about the space of the possible models and stuff like that. But data sets keep getting bigger, and the frameworks are getting better at parallelizing. And so I think it is starting to make more sense to do distributed training. It is easier to do. And the main distinction, when people say distributed training, they could mean one of 2 things. So one is data parallelism, and the other is model parallelism. So data parallelism means that you're kind of splitting up the data that you're trying to train on onto different GPUs, and it runs in parallel through different GPUs. And this is kind of what it looks like. The forward pass just goes through GPUs independently, and they don't communicate. And then the backward pass, the GPUs just have to sync up the gradients they've computed after every layer. And so this can slow it down, but it's not so bad. And like the forward layer is really fast. So what you really need for data parallelism is a way for GPUs to communicate very quickly. On a single machine, they communicate over the PCI bridge, and so it's very quick. In a setting where there's multiple machines, that's where you run into trouble. Like, how do you sync gradients across multiple machines? And that's it's important to kind of have multiple machines on the same network, and it gets very complicated very quick. But basically, what I want to get across is data parallelism does make sense. On a single machine, it's kind of a no-brainer. And the quote here is, for convolutional models, you should expect like a 2x or a 3x or a 3.5x speed up when you data parallelize onto 2, 3, or 4 GPUs. So it's almost linear, right? And then for recurrent networks, it's kind of the same, but it kind of depends on how long the sequence is. This is also from Tim Detmers. Model parallelism, on the other hand, is splitting up the weights that you're trying to train onto different GPUs. So in data parallelism, you split up the data, and every GPU has the copy of all the weights. In model parallelism, a GPU only has some of the weights. And that gets very complicated very quickly, and I just wouldn't recommend it. I don't want to talk about it. So TensorFlow distributed is something that when TensorFlow came out, it also had this TensorFlow distributed part to it. And they promised that it would be, it's like the promise was that it would be easy to do this kind of data or model parallelism with TensorFlow distributed. But it has not been an easy change to make for people. It required like re-architecting of the TensorFlow code. I don't think it works very well with Keras, but I think it's getting better. Horovod is something from Uber that essentially is like a simpler approach to distributed training using TensorFlow. And instead of like straight up TensorFlow code, they just used MPI, which stands for multiprocess. I don't know, what does it stand for? Oh, wow, OK. But it's a multiprocess communication framework where you have multiple processes. They could be on the same machine. They could be on different machines. They all communicate through this protocol with each other. And Horovod by Uber is essentially using MPI for syncing gradients instead of using like some TensorFlow distributed code. So it's usually less complicated. It seems to be a good speed up. I don't have personal experience with it, unfortunately. But I think some people in this room have experience with it. So maybe if you also have questions about it, maybe you can find each other, look in the queue. So the next thing I want to talk about is this idea of experiment management. So experiment management is the idea that like, even if you're running one experiment at a time, it's super easy to just lose track of what just finished running, right? You ran something, what data set did I train it on? What's the version of the data set? What are the parameters, like, what was the batch size? What was the learning rate? What was the network that I trained it on? And so what people do in practice is they open up an Excel spreadsheet or something, and they just say, this git commit, this data version, these parameters of the network, and then this was the validation accuracy. This is how long it took, whatever. So when running multiple experiments at once, then it gets like pretty impossible to actually keep track of all the results. And it'd be nice if we could just kind of automatically, like, not even have to worry about it. All we'd have to worry about is how do we launch experiments. But then from that point onward, we would just know that all the results are getting stored somewhere where we can access them. TensorBoard is the first kind of solution to this, and it ships with TensorFlow. And it makes a lot of sense for running single experiments or running experiments on a single machine because it syncs, it stores the logs to files, and then TensorBoard loads the files and displays them to you in a nice interface. It gets kind of unwieldy when you have multiple experiments going, potentially on multiple machines, potentially some in the cloud, some on premises. So different startups around a couple of years ago, I think, all saw the same problem. And I'll just go through a couple of them now. One is Losswise. And I would broadly describe it as just distributed, or TensorBoard in the cloud, right? So when you run an experiment, you just hook in a little Losswise callback so that every epoch or something, it returns its current training accuracy, validation accuracy, loss, whatever you want. When you started the experiment, it recorded the model architecture and the parameters that you had. And then it stores all of them on a website, which you can go to even years later and then review all of your experimental runs. Comet.ml is another such startup. They all started about 2-3 years ago. And then Weights and Biases is another such startup. And that's the one that we're going to be using in the lab. So you're going to see a lot more of this in pretty soon. So I don't want to spend too much time on it. The last thing I think is this idea of hyperparameter optimization. So the idea is let's say we're able to launch a lot of experiments, and we're able to keep track of the results. But now the challenge for us is to find the hyperparameters that are actually the best for our data set and model. The simple thing to do is just a grid search, right? So it's like search over learning rate, search over number of layers, search over convolutional filter size, search over dilation rate, whatever we want. You just put all of that in a giant grid of parameter combinations, and you just launch 100 experiments, and then the best row is going to win. Are there smarter things you can do? There are, and it's useful to have specialized software to kind of do that. So even if it doesn't do anything intelligent, it could be very convenient to just say, OK, on the command line, instead of saying learning rate equals 0.1, could I just say learning rate equals interval between 0.001 and 0.1, and then have the software kind of generate some points in between there and test them out? And what I'll do, since we're using Keras in the lab, is cover a couple of libraries. We're actually not using them in the lab here, but for a project to extend our code base, this could make a lot of sense. So I think the two most popular ones are called Hyperus and Talos. So Talos, this is kind of what it looks like. So what I highlighted here is it says model.add dense layer with params, and the param name is first neuron. And then I have a config file which says first neuron is a list that's 4, 8, 16, 32, 64, 128. And similarly for other params like activation and dropout. So what that means is I can launch this training on this model with this config file. And then Talos is going to figure out, it'll essentially start sampling points from the space of possible parameter settings, and it'll return the result. And it's called scanning, right? Hyperus is the same idea, except I think it tries to be a tiny bit smarter about it because it uses this package called hyperopt, which is useful for all kinds of Python machine learning things, not only deep learning. And it implements random search, which is what it sounds. Also this tree of parts and estimators. which is just a way to try to like kind of predict a little bit more about, like if I already tried, let's say I'm trying the number of layers, and I tried 1 layer and 10 layers, and 10 layers had a better result. Should I try 2 layers or 9 layers next, right? So that kind of thing, I can make a simple prediction that says 9 layers is probably going to be a better choice. There's also Bayesian optimization algorithms, but they're not implemented in HyperOpt. Where they are implemented is actually a software as a service called SigOpt, which claims that you can improve your machine learning models 100 times faster. You provide them with parameters. They essentially, they tell you, OK, use these parameters, and then tell us the results. So you do that. You tell them the results. And then they give you the parameters that you should run next. And it's just kind of like they keep giving you different parameters to try. Should be pretty good. I haven't personally used it, but I've always been interested. And then weights and biases actually has a built-in thing they call hyperparameter sweep, which is kind of a similar idea. You just say, OK, I want to sweep, let's say, learning rate from minimum of 0.001 to maximum of 0.1. And I'll say, when I launch my experiment, I'll do WNB sweep, and I'll give it that config file. I'll start an agent. And then the agent essentially gets like a job that it starts running. So WNB says, OK, I'm going to send this job, and then this job. And then the way they select the jobs to run is via some kind of prediction as to what's most likely to be a good parameter. And then they also give you an interface to visually inspect the results. I think Josh will cover it in a sample project. So the trend, when deep learning revolution really kicked off and people saw what it could do, they started writing all the software around it. And they saw that there was a lot of software that they had to write. And the reason for that is because it is really a fundamentally different way of writing software than what software developers are used to. Software developers are used to writing code, writing some tests, and that's it. With machine learning, you write code, you write some tests, then you label some data, and then your actual output is the product of data and code. And that adds like an incredible amount of complexity to the overall process. And the process is basically the same, and multiple companies have started converging onto it. And the way they, I guess, formalize best practices for this machine learning development is by developing a system that has kind of best practices built into every part of it. So that might take the form of a hosted notebook for development, and then and like a one-click deployment to many different machines to run experiments, sometimes with hyperparameter optimization built in. Then versioning the resulting models and easily reviewing the results in the table of results for archiving purposes. And then also actually deploying the trained model. So, and potentially also monitoring its performance. So I think the first one that was announced was this Facebook Learner Flow, Facebook's AI backbone. So it takes you from data to extracting features to actually running the training on a mix of CPUs and GPUs. So this would be that resource allocation part, producing the model, deploying the model for inference on CPU, and then making the actual predictions. And it has an interface for like storing the results of all your experimental runs. It has an interface for reviewing the type of model that you're running on, and potentially reviewing the results so that you can spot different things to improve. Michelangelo from Uber is the same idea, right? There's down here, there's offline features, meaning features that maybe nightly they aggregate for training, and online features, which are like things that come in as users use the app. And then it kind of guides you through feature extraction, training algorithm, which is distributed, storing the model in the repo, and then deploying the model. And it also has things like, can we look at the performance of the trained model? Can we look at the logs of the actual training of the model, right? Can we see a table of all the experimental runs? Google has an all-in-one solution, kind of. They have something public-facing, different offerings in the Google Cloud Platform. You have cloud storage for the collecting of the data, Cloud data flow, which lets you kind of pre-process and organize large amounts of data. TensorFlow for the actual deep learning modeling part of it. Then Cloud Machine Learning Engine for distributing your TensorFlow model onto many machines for experimentation purposes. And then also Cloud Machine Learning Engine for actual deployment of the trained model. So this is kind of the workflow: source and prepare data, code the model, train, evaluate, tune, deploy, get predictions, monitor predictions. So there's also been a paper called TensorFlow Extended, which is a TensorFlow-based production scale machine learning platform. And once again, it has all those parts: data analysis, data transformation, trainer, model evaluation, and serving. And I think this particular paper was never released as software, but the best practices from this paper made their way into something called Kubeflow, which is an open source project from Google. And it, once again, takes you from notebooks for like data science type of work to training the model in TensorFlow and scaling out to using Kubernetes to many GPUs, and then actually serving the model potentially in CPUs. Amazon SageMaker is the same idea from Amazon, customer facing. And then there's a bunch of startups that also try to give you an all-in-one solution. One of them is Neptune. So use Jupyter Notebooks in the cloud, quickly find and compare your best experiments, use Docker containers to specify your dependencies, and then run on our GPUs just by saying, Neptune send train with like. Floyd is another one, same idea. Paperspace is another one. It's the same idea. And Determine AI is a Berkeley startup that basically codes up that whole software stack, but not as a software as a service. Instead, they deliver it on-prem. So you can install their software onto your company's machines. But it gives you all that nice framework of like reviewing data, being able to get a model working, distributing training onto many GPUs, and then serving it. I like to think of the different things that these services provide across these different dimensions. Do they provide hardware? Do they provide a solution for resource management? Do they provide a solution for hyperparameter optimization, storing models, reviewing experiments, deploying the models, and then monitoring the predictions? So we can kind of go through the things we've covered so far and just see where they fall. So RiseML, yeah, they help you do resource management. They don't provide hardware. You bring your own hardware. Could be in the cloud, could be actual on-prem. They do give you hyperparameter optimization tools, and they store your models for you. Neptune does that, plus they give you an interface to search your experiments and review them. Paperspace Gradient, okay, loss-wise only gives you reviewing experiments. WNB reviews experiments, stores models, and does hyperparameter optimization if you want it in beta. Comet.ml, same idea. Determine.ai, hardware is on-prem, and then it does a bunch of stuff except for monitoring. And then Google Cloud ML Engine kind of does all of it for Google Cloud Platform. Amazon SageMaker does everything except for reviewing experiments, as far as I was able to tell. And then there's some other startups. So I think what you really should take away is this is the early days of deep learning, and people are figuring out and converging onto a process that makes sense for most teams. And this is what it looks like. Like these are kind of the steps in it. So it's your choice whether you build your own stack. You decide what hardware to get, how you do resource management, what you're going to use for hyperparameter optimization, what you're going to use for reviewing experiments. Or you sign on to Amazon SageMaker, for example, and they kind of give you a pre-built workflow for most of it. But the basic idea is that this is the workflow that we should all follow. And I think in a couple of years, there will be clear open source winners for all parts of the stack. But right now, I think you either kind of pick and choose different parts, or you sign on to something like Google or Amazon entirely. That is it from me. Do you guys have any questions? Yep.
So, very good talk, infrastructure and tooling. The one thing I still have an open question is that I happen to work for one of the boring companies that have a Java infrastructure, and so I don't see any mention of DL4J or Java or anything here.
Yeah.
And we do want to import deep learning models and incorporate them into our pipeline.
I think the principles are the same. Like, just because you're using Java doesn't mean you don't need to allocate jobs to GPUs or store your experimental runs or deploy your model. The specific software, I just don't know. Deep learning 4J seems to be like the winner in the Java space, but I don't have experience with it. But I would just say, now that you know the names of things, like, you can search and just say like Java deploying deep learning models and stuff like that. Sure, stuff will pop up.
Yeah, when did GL4J come up? There's nothing else.
That might be all there is. I don't know. Yeah. So TensorFlow.js is JavaScript.
Oh, sorry.
Yeah. So yeah, which is super cool. Well, yeah.
So it seems like when we say hardware, we are not talking about being tied into that hardware ecosystem. Like for example, here we say for Google, for some of these services, for flight, it's for Floyd, the last one, it's GCP.
GCP, yeah.
So yeah, but it seems like we won't be tied into that hardware if you're working like, from a software stack perspective.
Well, I think Floyd specifically, I think, built their service on top of Google Cloud Platform. So you can, when you launch experiments, it launches them on GCP GPUs. But you don't pay GCP, you pay Floyd. So versus something like RiseML, like let's say weights and biases. So weights and biases doesn't touch hardware because it doesn't do any resource management. So there you just send them experiments, as you'll see soon. They don't know anything about hardware. And then there's things like Amazon SageMaker, which only runs on AWS, right? And then there's things like RiseML, which does touch hardware, but they're agnostic as to what the hardware is. So you could install RiseML on top of Kubernetes, on top of Google Cloud, or on top of Amazon Web Services, or on top of your on-prem hardware. Yeah.
Just want to add a quick note about Java. I know there's like deep learning 4J
Uh-huh.
that supports both Java and Scala.
Oh, cool.
So that might be helpful for.
Yep. Yep.
Deploying when we do the model deployment in AWS, do we have components like Google Cloud?
Do we have what like Google Cloud?
The component?
Kubernetes in AWS? Yeah. You do, but it's a little more painful.
And they're coming with a managed service, EKS. It's in
Elastic.
They're coming with a managed
Yeah, the answer is basically yes, like a little more painful to use the actual open source Kubernetes, but there is something like Kubernetes on AWS.
If you
So-
just deploy it on AWS, though, just use the SageMaker deployment for stuff. I would not use Kubernetes for it.
So tomorrow we're actually having a whole lecture about deployment, so we can save that. So one last question, then we'll move on to the lab. Yep. Say it again? Kubeflow. I want to add it to the table. I haven't added it to the table yet. Yeah, sorry. Off the top of my head, I'm not able to check all the boxes. I have to look into it. Is that a last question? All right, one last question.
So based on your experience, what's the best cloud platform?
I think GCP is the best for machine learning right now. And I think the reason is partly because, like I said, they really see it as their differentiator with respect to Amazon. Like, how are they going to catch up to Amazon Web Services? Google Cloud Platform is just not nearly as prevalent. And I think their angle to dominance in the market globally is specifically via machine learning. So I think they're trying to do a really good job there. That's what I would say. But Amazon Web Services is also really great.
So, like in production environment, usually you mentioned the data locality. Is there any good answer to bridging the locality across the clouds, like GCP and AWS?
I don't think there is. Yeah. All right. Well, that's it for me. I'm going to hand it off to Josh to do the next lab session. So thank you.